In this video, I'm going to show you how to create a heap, and that includes things such as malloc and free. Alright, let's get started. Just a quick note, in the previous video I changed around the handle PS2 mouse function a little bit. One thing we just need to do is put some brackets around this data and bit value, just to make sure that this boolean expression gets evaluated correctly. Alright, so let's make a heap for our kernel. When you use standard C functions such as malloc or the free function, you're getting memory that's been allocated on the heap. So to use those functions, we need to create our own heap. So let's do that now. So in our source folder, we'll create a new folder and call it memory. And inside that memory folder, we can create a new file and call it heap.h. And we can create another one called heap.cpp. Inside of heap.cpp, we include heap.h, and inside heap.h we do pragma once and include standard int.h. Alright, so now we can do some for declarations of a couple functions. So we need our void InitializeHeap, and this one takes a void pointer to our heap address. The heap address is going to be a chunk of memory that we've mapped to a higher memory address so that it can be completely contiguous. We also need to take a size t, heap length, and this is the amount of pages that the heap will be initialized with. Now, in order to get size t, we're going to have to include standard def.h. There we go, so we've got our InitializeHeap function. Now, we need a void pointer malloc, and that takes a size t size. So when we call this function, we can pass in the size of a struct or a class, and it will return us a memory block that is the exact size of what we requested. And we also need void free and a void pointer to an address so that we can free the memory blocks once we're done using them. One more function that we're going to need is the void ExpandHeap, and this takes a size t length, and this expands our heap by allocating more pages to our virtual memory address when we run out of space. Right, now we need to define a struct, which is the header that goes at the beginning of each memory block that we allocate. We need to put this header here so that we can know how the memory blocks correspond to each other in the heap. So we'll do a struct heap seg header, or heap segment header, and the first member that we need is a size t length. The second one is a pointer to the next heap segment header, so heap segment header pointer next. Then we have a pointer to the last heap segment header. We need to keep references to these so that we can iterate through the heap and combine segments when we're done with them to reduce fragmentation. We need a bool free to know if this memory segment has been occupied by some memory. We have a void combine forward, which combines this memory segment with the memory segment in front of it, and we need a void combine backward, which combines this segment with the segment behind it. The last function that we need is a heap segment header pointer split, and this takes a size t split length, and what this does is split this heap segment into two smaller heap segments, with the first heap segment being of the size split length. Right, so now that we've done all of our declarations, we can jump on over into heap.cpp and start writing the implementations for the functions. So the first one we want to do is initialize the heap. So we'll do a void InitializeHeap, and this takes a void pointer to the heap address and a size t page count. Actually, we'll just copy this page count and paste it into the heap.h size t parameter as well, just to keep everything the same. Now we need to store a local variable of the heap address, so void pointer pos equals heap address. And now what we're going to do is map some memory to our heap address so that we can use it without producing a page fault. So for size t I equals 0, I less than page count, I plus plus. Now we can include our page table manager. So include dot dot forward slash paging forward slash page table manager. Now we can do g page table manager dot map memory pos, and then we need to include our page allocator. So include dot dot forward slash paging forward slash page frame allocator global allocator dot request page. Now I need to increment our position so that we start mapping pages contiguously across our virtual memory range. So pos equals caster to a void pointer 2 bracket size t, go out of 1 bracket pos plus 0x1000. So as you can see here, we're just adding 0x1000 to the address of pos. Right, now we need to calculate the size of the heap in bytes, so that's pretty easy. Size t heap length equals page count times 0x1000. And now we need to define a few global variables, so we have a void pointer heap start, a void pointer heap end, and a heap segment header pointer to the last header. We'll be using these two variables in the beginning, and we'll be using this one later on. Alright, so now that we have those, we can do heap start equals heap address, and now we can do heap end equals caster to a void pointer 2 brackets size t, go out of 1 bracket heap start plus heap length. And now we need to define the first heap segment header of the heap. So heap segment header pointer start segment equals casted to a heap segment header pointer heap address. Right, now our start segment's length, so the length of the segment, needs to equal the heap length, which we calculated up here, but we need to take the size of the heap segment header. Because this heap segment header is taking up space in the heap, and if we don't account for that, then we will have overflows. And since this is the first and only segment in the heap, the next segment equals null, the last segment equals null, and it is free. And since it's the first and only segment in the heap, it is also the last segment in the heap, so we can set the last header to the start segment. Alright, now that we have our InitializeHeap function, let's go to kernel-util.cpp, and after we prepare the memory, we can now initialize heap. Of course, we're going to need to include our heap.h, so at the top we can just do include memory /heap.h, and we can initialize our heap at some arbitrarily large memory address to stay out of the way of virtual memory. So we can do a void pointer 0x and then 4 zeros, a 1, and then another 4 zeros, another 4 zeros, and then 3 zeros. So it's a very large number, so it will stay out of the way of pretty much everything. And let's initialize it with 0x10 pages. Now, just to make sure that we haven't broken anything, we can run that, and if we don't get a page fault, then that means we've mapped all of our memory correctly. Alright, so as you can see, it's working fine, so that means all of our memory has been allocated correctly, so that's pretty good. Alright, so now that we have that, we can go on and start writing the implementation for malloc. So we have void pointer malloc size t size. Pretty simple. We should round our size upwards to a 64-bit number. So if size modulo 0x10 is greater than 0, which means it is not a multiple of 0x10. So this is just 128 bits. It's a nice number to be working with and helps us when debugging, in my opinion. You can do 0x08 as well, which will keep it as a multiple of 64 bits. So if it is not a multiple of 0x10, then we round it down. So size minus equal bracket size modulo 0x10. And then size plus equals 0x10. So we're rounding it down and then adding the multiple so that we have enough memory to contain whatever we're putting into this malloc function. Now, if size equals 0, then obviously we need to return null because we don't want to do anything then. Now we can start iterating through all of the memory segments in the heap to find one that is free and has enough space inside of it for our memory block that we're requesting. So we can get a pointer to a heap segment header current segment equals casted to a heap segment header pointer heap start. So we're getting the very first heap segment header. Now we can enter a while true loop and do if current segments free, and then if current segments length is greater than size, we can do current segment dot split size. Now in the split function we will make sure that we have enough space for a new heap segment header, so we don't need to check if there's enough space in this branch here because we're going to do it inside this split function. Then we can set the current segment's free boolean to false because it's no longer free, and then we can return the current segment memory address plus the size of the memory segment header. So return casted to a void pointer, 2 brackets casted to a uint64t, go out of 1 bracket current segment. So we're getting the address of the current segment as an integer, and then we're adding the size of heap segment header. Now I personally just prefer to do integer maths when adding addresses together. You can probably do a pointer maths and just do not cast it to a uint64t and then +1 and it will return the same result, but I prefer to do it like this. Alright, so we've checked if the current segment's length is greater than size, but if it is equal to size then it should also be a correct return. So if current segment's length equals size, current segment's free boolean equals false, and then we can return the same as what we did up here. Alright, now we can go out of these two if statements and then go to the bottom. So if current segment's next segment equals null, then we need to break, and this is the only way we can get out of this loop is if the next segment is null. And then if it is not null, meaning there is a next segment, we can move the current segment pointer forwards. So current segment equals current segment dot next. So now this loop iterates through the entire heap and returns a segment that is of the correct size, and then splits it up if there's room for another segment after it. But what if there is not enough room with the heap? Well, then we need to extend the heap and pass in our size. Now we need to create this ExpandHeap function, which we will get to eventually, and then we can return malloc size. So what we do is we extend the heap by the size and then recursively call malloc. This will only ever be called once because ExtendHeap will, in one pass, allocate enough memory for the next segment that we are going to be requesting. Right, now we need to create this ExtendHeap function. So in heap.h, we've already created ExpandHeap, so we'll use that instead of ExtendHeap. Just a bit of a typo there. Alright, so now that we have malloc, we can test that. So alright, so now back in kernel.cpp we can test this out. So we'll need to include memory/heap.h and then make sure that we're on a new line, so global renderer.next, and then we can do global renderer.print to hstring casted to a uint64t malloc 0x100. So we are requesting a block of memory of size 0x100. Alright, so we have undefined reference to heap segment header split and expand heap, so we quickly just need to create some stub functions for those. So we have heap segment header pointer, heap segment header : split, size t, split length, and this will just be a stub for now, so just leave that as it is. And we also need to create a stub implementation for void expand heap size t length. Alright, now if we try and run that again, let's run that and see what we get. Alright, so as you can see, our memory address is our 10000 etc 20, and that's because that 20 is the size of our heap segment header, so it's given us a block of memory directly after that heap segment header. Now we can only currently allocate one block of memory before the entire system shuts down, because we haven't completed our implementations of any other functions. So let's get into that now. So let's implement the split header function next. So what we need to do first is check if the split length is less than 10, and if it is, then we can return null. Now we can work out the length of the new segment that we're creating. So size t split seg length equals length minus split length minus size of heap segment header. Actually, this should probably be a signed integer. So I'll do an int 64t so that we can check if this goes below 0. So if the split segment length is less than 0x10, then we can also return null. So basically, if the split length, which is the size of the block that we want to split, is less than 10, then basically there's no point splitting it because it's so small. And if the size of the new segment is less than 0x10, then it is also too small and there's no point in splitting it. Alright, now that we've got those two checks out of the way, we can create our new split header. So we have a heap segment header pointer new split header equals casted to a heap segment header pointer, and we can take the size t casted address of this plus the split length plus the size of the heap segment header. So what we're doing here is calculating the address of where the new split header will go. So now we need to move some pointers around. So the next heap segment header of the current heap segment header's last heap segment header now needs to equal the new split header. The new split header's next header needs to equal the next header of the current header. Now the next header of the current header needs to equal the new split header. Now the new split header's last split header equals this, because we're putting it directly after the current header. We need to set the new split header's length to the split segment length, and we need to set the new split header's free boolean to the current free boolean. Now we need to set the length of the current header to the split length, which is the one that we passed in at the start of the function. So just to comment those out, we need to set to its new length. So we're moving around a lot of values there, but we're just making sure that all of the blocks in the heap correspond to each other correctly. Right, now just to keep track of the last header, we can check if the last header equals this, meaning that the current heap segment header is the last header, then the last header now must equal the new split header, because the new split header is coming after the last header, so the previous last header is no longer last. Then we can return new split header. Now if we jump back into kernel.cpp, we should be able to call malloc several times in a row, because we should be successfully splitting our heap segments into smaller segments after we've taken out the chunk that we need. So on 3 separate lines, we can print 3 different malloc addresses and see what the result is that we get. Alright, so as you can see, we have 020, 140, and 260. Now we're requesting a size of 100, but we're getting the size of the heap segment header added on. So each time we're requesting 120 technically, and that's why every iteration is increasing the address by 120. So that's working correctly. We're splitting the segment as it should be done. But now we need to make sure that the heap doesn't run out of space, so we need to implement the ExpandHeap function. Right, now we need to round this length up to a full page size. So if length modulo 0x1000 length minus equal length modulo 0x1000 and length plus equals 0x1000. Now we've rounded length up to a multiple of the page size, we can go on and actually create the new memory. We can calculate the amount of pages that we're needing to allocate by doing size t page count equals length divided by 0x1000. And before we go ahead and move the heap end pointer, we just need to store a reference to the current heap end as a heap segment header pointer. So we have a heap segment header pointer new segment equals casted to a heap segment header pointer heap end. So we're putting a new segment at the end of the current heap. And now we can allocate the new pages. So for size t I equals 0, I less than page count, I plus plus. Now we can do g page table manager dot map memory heap end global allocator dot request page. Now we need to move heap end forward by a page size. So heap end equals casted to a void pointer 2 brackets size t exit 1 bracket heap end plus 0x1000. So now we're just adding the page size to heap end. Now that we've allocated the new memory, we need to set up the correct values in the new segment header. So new segment dot free equals true, new segment dot last equals last header, the last header's next value equals our new segment, and now we need to make the new segment the last header, so last header equals new segment. Now this new segment is at the very end of the heap, so the new segment's next segment equals null, the new segment's length equals length minus the size of a heap segment header. And now we need to do new segment dot combine backwards. So that means we combined the last segment that we just created with the segment behind it to create one big block. Alright, now that's all fine and dandy, but we need to actually implement these combine backward and combine forward functions now. So let's do that. So we have void heap segment header colon combine backward. And all this does is call the last segment's combine forward function. So if last does not equal null and last is free, then we can do last dot combine forward. Now we can implement the combine forward, so heap seg header colon combine forward. Now this is a little bit more full on than combine backwards. So if next equals null, return, because we don't want to combine forward if there is nothing to combine with. And if next is not free, then return. Now we can check if the next segment is the last header. And if it is, we are now combining the next segment into the current segment, so the last header now equals this. Now we need to update the next segment's last segment to be equal to this. So if next dot next does not equal null, then the next segment's last segment equals this. Now I need to calculate the new length of the current segment. So length equals length plus the next segment's dot length plus the next segment's length plus the size of heap segment header. Now we're adding on the size of the heap segment header because this next block, including its own heap segment header, is its own length plus a heap segment header. So we're consuming this heap segment header and the entire length of the next segment to create the new length. Alright, so now that we have combined forward, we should be able to expand the heap. So let's do a test now. So we have initialized the heap to be 0x10 pages in size. So if we allocate lots of memory, so 2 lots of 8000, then we should fill up that entire memory segment. And then if we allocate a 100 on top of that, if it works, then our heap has successfully expanded. So let's run that and see what we get. Okay, so now as you can see, the first segment is allocated at 20, the next one is at 8040, and then the next one is successfully allocated to 10060, which is greater than the size of our initial heap. So our heap has expanded successfully, so that's pretty good. Now there's one last thing we need to do, and that is to implement a free function, because if you have memory allocation without the ability to free it, then you're just going to have memory leaks everywhere. So let's do that now. Now with all of the functions we've created, creating a free function is really straightforward. So void free takes in a void pointer address, and this address is the value returned by the malloc function. So we need to do heap segment header pointer segment equals caster to a heap segment header pointer address -1. Now we need to -1 because we need to get the heap segment header, not the memory allocated block. So now we can set the segment to free. And then we can combine the segment forward. And then we can combine the segment backwards. Right, so now we can test the free function. So back in kernel.cpp, we can save this malloc call into a variable. So void pointer address equals this malloc call. And then we can paste our address straight into this function. And then after everything, we can free this address. And then do another call to malloc, and we should get the same address as this address here. Alright, so as you can see, we have 208040, this really big one, and then we have 8040 again, because we freed this block after we allocated this one. So the free function's working properly. We can allocate memory, free memory, and expand the heap when it's needed. So I think that's a pretty good implementation of a heap. Now there's a lot of optimizations we can do. It's fairly slow once the heap gets large because it needs to iterate through all of the memory blocks. But as just a general implementation, I think that's pretty good. Alright, as always, thank you for watching, and I will see you next time. I just wanted to say a quick thank you to my patrons. We have the Tier 2 patrons Cole Fodorado, Mad Max, Jewel Kem, Bobby Addison, Jim Borden, Rizix, and Daniel Cosper. And thank you to my Tier 1 patrons Adam, Kenneth Looney, THXTNT, and David Gonzalez. I really appreciate any support you can give.